So Phil is a PhD student at Cornell, advised by Ari Jules, and he is going to talk to us today about DeFi composability. So take it away, Phil.
Yeah, can everyone hear me okay? I know I was having some issues yesterday. Good, great. All right, hi everyone. I'm here to talk to you guys about DeFi composability. I'm sure we've heard this buzzword DeFi at least once or twice this conference. And I say that because I've said it at least once or twice this conference. So we're going to talk about the framework we're building here at IC3 for sort of building and reasoning about these money Legos in permissionless blockchains. So in TA school, at some point, they told me that there's a class of person who learns best when you show them an outline first. So that's what I will now do. So we're going to talk about what DeFi composability is. We're going to show some very, very basic DeFi contract examples and what we call basically Legos, to sort of give you some intuition on how DeFi contracts work and execute, as well as a few kind of common pathologies that come out of them. We're going to talk about MEV, or Miner-Extractable Value, and how that's relevant to sort of DeFi, as well as all of the composability subjects we'll touch on today. We're going to talk about why arbitrage, software exploitation, software verification, this concept of MEV, and DeFi composability can all be studied through the same lens and with the same sort of scientific tools. We're going to define smart contract composability at sort of a high level. And then we'll talk about how we actually tackle this, how we build these models and reason about these complex protocols that people are trying to build. So let's begin. I thought it would be fun to start with some really pretty pictures of things people make out of Legos. So humans are really cool. If you give them a bunch of stackable blocks, they'll come and surprise you and build all sorts of art. So that's some dude with a chest spilling out. This is like a really pretty tiger. This is like a whole city built out of Legos. But I think still the coolest one is this one, which is my mood in 2020 built out of Legos. So I think that's really fun. All right, great. So let's talk about our first Lego, and I'm going to call this Lego Monoswap, not at all named after or inspired by a real protocol. And the goal of this Lego is going to be to allow for an on-blockchain exchange of Ethereum and US dollars with no counterparties. If you were paying really close attention to my project intro, you can tune out for like 2 minutes because it's the same example. So let's say we have a situation where Alice and Bob want to come on a blockchain and kind of do their own trades. So Alice here wants to sell 1 ETH and Bob wants to buy 50 cents worth of ETH. Alice wants to sell for USD kind of implicitly here. And we're using a non-gendered Alice and Bob, so get used to that. So what can Monoswap do? Basically, what Alice and Bob will do is they'll come to this Monoswap contract, which is this object that exists on the blockchain, shown here as a green heart. And that Monoswap contract in the blockchain state is going to hold some balances of the various assets that it's designed to exchange between. So here you see ETH and USD held in sort of a 1-to-1 ratio. And what this Monoswap is going to do, and I apologize I didn't make this clear, I know it was confusing last time I said I gave this talk too, but what Monoswap is going to do here essentially is keep this product constant between the ETH and USD kind of balances. And that's this K over here. And here you can see K is 1 because 1 times 1 equals 1. So that's what's called an X times Y equals K market maker. So how is this useful to exchange ETH and USD, which is the goal? Well, Alice can come to this contract and send it 1 ETH because she wants to sell 1 ETH for US dollars. And what will happen to Monoswap now? In the current blockchain state, sort of after Alice sends this transaction, you'll see that Monoswap now has 2 ETH and 1 USD for X times Y equals K of 2. Now, the goal of the Monoswap contract is to sort of hold that K constant at 1 at all times, no matter how many trades kind of happen across it. So that's why we kind of drew it red here, because this is a bad state for the Monoswap contract to be in. And to get back to a good state, what the code of this contract is going to do is send 50 cents of USD back to Bob. That's going to leave the contract balance now at 2 ETH and 50 cents of USD, and K again, which is product, is 1, which is what we want. All right, so Alice, sorry, I might have said Bob, but Alice has sold her 1 ETH. She's happy. Now let's go to Bob. Similarly, Bob kind of sends $1.50 to this contract. Now you have 2 ETH and 2 USD in there for a K of 4. And to rebalance for a K of 1, what you actually want is 0.5 ETH and 2 USD, because that equals 1. And to get to that state, the contract will sort of send Bob back 1.5 ETH. So now Bob is happy, his trade has executed. So what have we done? We've actually built a Lamborghini for exchanging ETH and USD, just kind of out of Legos. This is pretty amazing, right? Any user can come to the blockchain at any time. There don't have to be any other users trading in the system. They don't need counterparties. There doesn't need to be some centralized service kind of spinning up infrastructure and processing their trades. They can just come to this Monoswap on the blockchain and sort of do their exchanges anytime and basically get the market price. Why do they get the market price? Because if the contract is offering something other than the market price, there's kind of an arbitrage incentive for people to come and arbitrage that back. So great, that looks great. That's like exactly what we wanted to do. But what's the problem with this? Let's consider a different world in which Alice and Bob still want to buy, Alice still wants to sell 1 ETH and Bob still wants to buy $1.50 of ETH. And again, we start the Monoswap contract with 1 ETH and 1 USD. So in this world, kind of what's going to happen is that Bob is going to send his 150 USD, kind of like he did over here, into the contract, which is now going to have 250 USD and 1 ETH for a K of 2.5, which is not 1. To restore its K, it's going to send that 0.6 ETH back to Bob. Once again, now you have 0.4 ETH and 2.5 USD for a K of 1. And then Alice is going to come and send the contract for ETH, raising the contract's ETH balance to 1.4 with a K of 3.5. And so to restore the K of 1, the contract is going to send Alice about $1.80 in USD. And now you're left with about 1.4 ETH and 71 US dollars in the contract, again with the K of 1. So what happened here? In these two different worlds, and the only difference being the exact same transactions that needed to be made on a chain executed in a different order, you have two very different outcomes. So on here on the left, Bob clearly did better than he did on the right? He sent 150 USD and he got 1.5 ETH. Over here, he got only 0.6 ETH, which by comparison looks like a pretty major ripoff, less than half as much. On the other hand, Alice highly prefers this execution on the right over here, because in this execution on the right, you can see that Alice got $1.80 for her ETH, whereas over here, she only received 50 cents. So who picks these winners and losers in these DeFi kind of protocols? Well, the miners do. And this is kind of something we wrote a paper about a year ago. We kind of analyzed what we call the Miner-Extractable Value game. And what Miner-Extractable Value is, or MEV, is a measure of how much cryptocurrency a malicious miner can extract from a system by reordering, censoring, and inserting new transactions or behaving maliciously on the network. And the MEV is oftentimes a number in sort of a specific system state, so it's something that we can actually measure. It's worth being said that when we put this out, I kind of actually regretted calling this MEV because people say, well, this value is being extracted by bots, not by miners. That's not really what MEV is. So it's Miner-Extractable Value, able. It's value that is able to be extracted by the miner. So in any case, in sort of Ethereum today, when you have an arbitrage bot that's kind of coming on and interacting with systems like Uniswap or MakerDAO or other DEXs or lending protocols, that bot ultimately is in a weaker position in terms of the power structure of the network than the miner, because the miner in a permissionless network has access to the entire action space of the bot, plus the ability to control transaction inclusion and ordering. So kind of the ultimate security metric for a smart contract that we look at is the Miner-Extractable Value. And here we also use the word validator because I'm aware they're called validators in some systems. There is no difference. So that's sort of the ultimate metric in any permissionless system, because the miner or the validator is ultimately the most powerful entity in that system. So this is kind of a superset of all the other kind of security metrics for the system. And formally, we're going to define this MEV as the amount of ETH a special miner account. Sorry, this words got reordered. A special miner account can, given a set of user transactions T, an initial state S, and a set of contracts C. Yeah, looks like my keyboard was messed up, so it's how much ETH a miner can gain, obviously. Given sort of transactions that users have made that are available to be censored or reordered, an initial state that kind of has the blockchain state when the miner starts playing this game, and a set of contracts that are available for the miner to use. So what we thought we were building with Uniswap was actually a Lamborghini, but because of sort of this amazing variance in outcomes that users can get in the systems, what it really looks like is kind of something more like this. And I would argue that that's not the greatest thing. So one high level point that's kind of interesting here that I kind of made at the beginning of the presentation, and if there's one takeaway that I want you to get from all my ranting here is kind of this one, it's that DeFi systems and these new financial systems we're building are unique from Wall Street systems in many ways, because you have these highly deterministic rules that are operating on the blockchain, you sort of have a bunch of these kind of previously disparate areas of study that have kind of converged into one single area of study in DeFi systems and in blockchains. So one of these areas of study is arbitrage, and traditionally that looks like bots on Wall Street who are highly peered with extremely fast networks, trying to sort of insert their own orders or manipulate network order in a way that's profitable for them. Another thing here is exploitation. So black hats who are doing things like trying to find vulnerabilities in production systems, trying to hack things like the US Fed or JP Morgan Chase, or whatever that might be. Also verification from the software security literature. So there's like a wide range of study on what it means to prove a program correct and what it means to prove properties about a program. This concept of MEV that we just discussed, which is how much money can a miner make from the system, and this concept of composability, which is like how secure are these DeFi Legos that we're building, how able are we to combine multiple Legos without introducing new attacks or without breaking fundamental properties of our systems. So what I'm arguing here is that this is all, in terms of blockchains and smart contracts, really the same technical problem. And the technical problem is exactly the problem of MEV. And again, I copy pasted it wrong, so sorry that it's confusing, but it's essentially from some starting state, S, how much kind of cryptocurrency / money can you extract by exploring the possible state space of outcomes and sort of picking the one that's most advantageous in MEV to the miner, or potentially you can optimize for whatever utility function of that state space you prefer. So really all of these kind of different problems are just a state space search on a set of deterministic rules, which is exactly what program verification is in many ways. So what we're going to do now is kind of combine all of these things and bring them together. So the first thing we're going to talk about is how composability relates to MEV. So I want you to remember the example we showed before earlier with Monoswap. And let's think about how much MEV a malicious miner can extract from this system. So obviously the most amount of MEV a miner could ever possibly extract from this system is if it drains the entire Monoswap contract and steals all of Alice's and Bob's money, so they each get 0 in this transaction. And that MEV would be 1 ETH plus 1 USD plus $1 plus, sorry, 1 ETH plus 1 USD plus $1.50 plus 1 ETH. That's 2 ETH and $250. Now let's say we enter a world where Carol and Dave come along, and Carol and Dave are gamblers. They like placing bets. And they're also traders who trade on sort of the fundamental price of ETH against US dollars. So Carol and Dave kind of want to make this own bet just between themselves and not anyone on the rest of the network about what the price of ETH will be. So what they might decide to do is kind of put up a contract that looks at the ratio offered by Monoswap between ETH and USD, which in this automated market maker setting is a proxy sort of for the price that's going to be offered on the next trade, as we saw in those ordering examples. And if Carol thinks ETH is worth very little, what that means basically is that this contract is going to end up with a ton of ETH. So even small amounts of tokens will be able to purchase lots of ETH from this Monoswap contract. So in that case, this betting contract will look at this ratio, and if there's more ETH than USD, it will pay Carol. And otherwise, it will pay Dave. And this sort of accomplishes the high-level bet that Carol and Dave are trying to do here. And let's say they each send 1,000 ETH to this contract. They're whales. They want to make like a big bet, and they don't waste their time on small fish. Well, now what you're looking at is instead of having a 2 ETH MEV, you have an MEV that's like thousands of ETH. Obviously this is an absurd example, but what this basically shows fundamentally is that when you're reasoning about the security of your DeFi Lego or your permissionless financial instrument, you also have to think about all the ways people are going to use it and all the other dependencies that could potentially be introduced on your system. Why? Because once this MEV has been created, even though there aren't any changes to this original contract or this original scenario, the miners now have a much higher incentive to break this Uniswap price in order to manipulate the bet between Carol and Dave, which reduces the security of this sort of, Monoswap instrument for its users and makes execution very unpredictable. And we also talk about in Flash Boys how that's a problem for sort of the entire consensus algorithm. In taken to the extreme, this will end up with miners sort of fighting each other to extract this MEV in a way that destabilizes the whole blockchain and leads to rollbacks and reduces the value of confirmations on chain. Right, so you can see there miners have way more incentive to attack. So what does this show? This kind of highlights what we mean by composability in DeFi. And what we mean by composability at a very high level is when the execution of other contracts in the system outside of your own contract affects the execution of your contract, either by improving its security in a kind of synergistic effect, or in a negative case, like we just saw with Pricebetz, by reducing your security by either eroding security guarantees or providing incentives for attack. And so remember the definition of MEV that we showed you earlier, and the way we sort of think about composability here at IT3, and you can watch out for a new paper that's going to be coming out on a more formal definition, as well as kind of a lot of definitional questions around this work in the next few weeks. But the way we think about composability is to say that a set of contracts C composes with a set of contracts C prime in a set of initial states S star if the set of contracts C combined with C prime does not have more MEV than the original set of contracts. So basically, by adding these new contracts in this initial state, you are not increasing the amount that a miner can extract from the entire system. And this is a very strong property. It's a very strong kind of non-interference property that says that, like, essentially no new exploits, no new arbitrage, and no new kind of perverse incentives are introduced by the sort of combination of these protocols. There's a few caveats here. So by more MEV, and I apologize, I overloaded the asterisk here. What was I thinking? But by more MEV, what we mean is it's bounded by some function. And we also say kind of a contract achieves universal composability if it's composable with all C prime and all S star. So basically, no matter what you do on the blockchain, your contract will not expose additional MEV. And once again, we also have this little caveat here, which is that in permissionless systems, we are generally interested in the MEV because it's the most strong form of attack. But if you do have permissioned elements in your setting that open up attacks to parties other than the miner, you can just look at the general EV with regards to the actions kind of able to be performed by those parties. One example of that would be like a quorum-like blockchain, and another one would be a permissioned oracle kind of design. All right, so let's go back to building the Lamborjini. And notice that I say Lamborjini here because I actually have had slides taken down for trademark violations, and it's so annoying. So to build the Lamborjini, you know, we got to build the wheels first. We got to kind of discover the wheel and figure out all of these different types of wheels and what they do. Because we know as car people that really the wheels make the whole car. You know, like look at these wheels versus those wheels. That's a big difference in wheels. And really that's kind of the difference you're going to see in these DeFi deployments. So how do we do this? We start with the code. So this is the code for Uniswap v1. It's written in Viper and it's available on the internet to swap Ethereum into some token. And basically what this will do is it will look at the balance of Uniswap. It will calculate a price that it should get for the buyer. So this is like the arrows I was showing you before, how much to send back. And then it'll sort of transfer the tokens and log that a purchase has been performed. And there's also this kind of function here called getInputPrice that has a mathematical specification, essentially, written as Viper code of the formula to calculate how much money Uniswap kind of sends back every time. Essentially, those arrow formulas we were showing you before. And you can see there's some weird constants here, like it multiplies the input amount by 997. Adds the fee, multiplies it by how much output Uniswap has in its balance, multiplies that by 1,000, and returns the ratio basically. So if you actually do this algebra, and there's a report available by runtime verification where they prove that this is actually the case, this does implement the X times Y equals K market maker that Uniswap promises to. So what do we do in order to study this? Well, the first thing we do is we come up with a mathematical description of this. So this it looks mathematical, but really it's not because it's Viper code. So it's prone to all of the semantics of Viper, including, for example, rounding in arithmetic, exceptions, overflow behavior, size limits, gas semantics, and etc. So we take all that out and only look at kind of the core of the mechanism that we want to study by formalizing that mechanism as a mathematical object. You can see here this Uniswap mathematical object basically looks at the balance of the Uniswap contract in the input and output, calculates that ratio. Here you don't have the 997 constant for like weird technical reasons, but don't worry about that. and then sort of affects the balance changes in the state that are required to maintain that x times y equals k invariant that we talked about earlier. And then we actually take it a step further. So once we sort of build this set of Legos that are these mathematical descriptions of DeFi protocols and their core essence, we write these in a very formal and computer executable modeling language known as the K framework. If you do Ethereum formal verification, you're probably familiar with the K framework and KEVM. It's the framework that's used in many cases to reason about the security of Ethereum contracts. And what we do with the K framework is we essentially define this. Just in terms of pure mathematics, where the times and plus things here have integer mathematics semantics, we define what does it mean to execute a Uniswap trade. So here we say executing a Uniswap trade where address in some token input swaps some amount of input for some output token with a fee, gas fee. What that will do is it will debit the input address by the input amount. It will give the input address the output amount calculated using the x times y equals k formula you saw in the Uniswap code slide. It'll do kind of the converse for the Uniswap contracts, and it'll also debit the gas fee from the original account. And then the side condition here that this is only allowed to occur when the user balance of initiating this trade exceeds the trade amount. So once we've defined Uniswap using a few different rules like this that are kind of very modular, very human readable, and very mathematical, we can throw that model of Uniswap at the K framework and get a whole bunch of magical tools that are really, really cool. And like my job here is to get you really excited about those tools because they are really cool. So here's one tool. So the first thing we can do is we can sort of download from the blockchain data about how Uniswap has been trading various tokens. So this is an English language representation of what Uniswap has done for this obscure token called the Mecenas art token, or ART, with address 0xFEC, blah, blah, blah. So from Google BigQuery, we pull all the Uniswap contract events and we parse it into sort of this English language list of all the things that have happened from the beginning of time in this contract. So here, for example, this large number, which represents an ETH address, if you convert it to hex, added, 1,000 tokens or whatever this ends up being, and 2 ETH of liquidity to this token address, which is this Mecenas token address. Then this other address in 0, which means they were swapping in ETH, swap some amount of input for that amount of output with some fee, right? And then what we can do, so this is what we call a program, and it's basically a problem instance for our MEV model. And basically what we're saying here is that if in some initial state, which we define, the miner sees these transactions, we're now able to, using the K framework symbolic execution features, kind of programmatically reason about the best strategies to take on the state space, as well as the optimal MEV and the bounds on sort of this MEV. So there's this kind of Python interface we provide for this tool set where you can feed in these programs that we parse from the chain, and you can tell it to do things like find bounds on various, you can see up here, Uniswap lower bound. They're just symbolic expressions sort of on the system state. So here you can say basically, find me the Uniswap upper bound, which is the highest amount that Uniswap can end up with, the most ETH that can end up in the Uniswap contract, such that basically for all execution possibilities in the state S, the account Uniswap in 0, which is ETH, has less than or equal to this integer %B. And then if you give that sort of claim to our framework, it's going to use SMT solvers on the back end, specifically Microsoft V3, through the K framework to sort of give you this output that will show you kind of the final state, which maximizes the claim that you wanted to make. So this is the final state where Uniswap, given these transactions on Mecenas token, ends up with the most ETH, as well as the block. So this is sort of the miner block that would be required to end up in that state. So we'll give you sort of a counter example. So if you try to prove like my program has no more than $1 million of MEV, it'll come and say, no, actually you have $1.5 million of the MEV given these transactions in this state. And here is the sort of minor choices that would have led to this MEV. And because this is done using symbolic execution, the output is actually, despite being somewhat inefficient to calculate, it is a full formal proof that these are the tight bounds given the correctness of the model. So why are we using the K framework? Well, the vision of the K framework, and I won't go too much into it, you can read about it online if you want, is to sort of have this framework where languages can be defined in pure formal mathematics, and then language tools like compilers and program verifiers can be automatically compiled from these mathematics without people needing to sort of specifically put in the effort to manually write tools. So why do we want to do this for DeFi? Well, because we want to create this core, very, very modular set of models, like the one I showed you for Uniswap. We also have ones for MakerDAO, and we're working on ones for quite a number of other DeFi protocols. So K allows us to do this in sort of a modular way, where we can pick and choose sort of which Legos we want to reason about. It's also human readable, as I kind of showed you. The sequence of steps is very clear to any developer or mathematician. It's executable, so we can generate an executable version of the model and replay all of the transactions that we've seen on the network to make sure the model is actually accurate and accurately corresponds to the network. And from this set of open source models, which is going to be reviewed and validated by the community, hopefully, we can use K to automatically compile all these amazing tools, including this optimal strategy finder that I just showed you, which will find optimal strategies for the miners, and which can be used to inform development of trading strategies and secure contracts. It'll also give us these interpreters that we can use to replay the blockchain and validate that our models are correct. This runtime monitoring sort of software that we can deploy on the chain itself and use to receive alerts whenever something that diverges from K's sort of implicit model has happened, as well as a variety of other sort of logical reasoning features that come with the very formal mathematical backend that powers K. You can see also more on the EVM semantics repo under K framework. There you can see the full K semantics of the Ethereum blockchain and the EVM, which is the most complete formal semantics currently available. You can also use this to prove formally that the models that we're developing for DeFi protocols actually correspond to the real contract code that's being deployed on the chain. There are also more abstract models that have already been written in K that we can sort of use, including ERC20 models. And a variety of models for various smart contracts, including developed by the Ethereum Foundation and other companies. So for more info on K, you can go to runtimeverification.com. You can look at their blog. They have all sorts of articles about why you should choose K over COP and why K is the right tool for verifying smart contracts and all these things if you're still skeptical. So the TLDR of my talk is to build a Lambo. We have to understand the wheels first. That's what we're trying to do here at IC3. We're trying to understand the wheels in a sort of tractable way that's more in-depth and more rigorous than is being done in industry and is being done in the IPO boom. And we welcome your help in helping us build the Lamborghini anytime. Feel free to reach out to me on Twitter. And thank you to all our partners for supporting us, being amazing, funding this research, and you know, continuing to keep things exciting. I think I have 2 minutes to take questions before we have to go to the panel. So maybe one super quick one.
Okay, thanks, Phil. So we do have one question in the chat. This is from Alex. It says, it does not seem that there are many examples of miners actually maximizing their utility. Why do you think that is? Are they lazy?
Well, you know, I just had two of my amazing panelists join, and this might be a good segue. Before we start the panel, I will also let them answer this question because they're both experts in this field. I think what I would say is miners are not extracting the MEV right now is because it's a lot of engineering effort and they don't have the in-house expertise to sort of build those tools that they need to extract the MEV. You know, incentive-wise, obviously their incentive is to do it. One other possible explanation is that they're altruistic and they're just very nice. And they love Ethereum so much that they wouldn't want to mess with something like Uniswap because they care more about Ethereum as a whole.